Previously, we had shown that a conservative force is one where the work done connecting any two arbitrary points along all possible paths that connect those points is the same. And that was a lot of work, but now we get the payoff. And the payoff is that we found that since the only thing that would change how much work a conservative force did was literally where the endpoints themselves were, this gave us hope that we could define a function that only depended on the position of the particle. And that function gets called the potential energy. So for any particular conservative force, the potential energy is defined to within its change. We only can say that the change in the potential energy is defined to be equal to the negative of the work done by the conservative force in question. So for a conservative force. And the deal is that we are absolutely 100% free to choose the function for the potential energy. As long as that function satisfies that the final value minus the initial value equal the negative of the work done between the 2 points. So for instance, for gravity near a planet's surface, the conventional choice is to say that the potential energy is equal to m times g times the object's y coordinate. So what this really is, and this is a hallmark of all potential energy functions, is they depend on the force and they depend on the configuration of the players. For instance, with gravity, the force is gravity. The configuration of the players, that's just the separation between the Earth and the object. It will have to wait a while to show that we can turn that into mgy for an object near the surface of a planet. But for now, just trust me that that is true. So this is the conventional choice. So let's just see that this works. So we require that the change in potential energy be equal to minus the work done by gravity. Okay, in the previous video we found that the work done by gravity was minus, so we have two minus signs, m times g times y final minus y initial. Similarly here, this is going to be final minus initial, so the final potential energy would be m times g times y final, and the initial is m times g times y initial. Well, all right, minus a minus is a plus. I can group around and get mg y final minus y initial equals mg y final minus y initial. Check. So what that means is that this function is a good choice. And all we can truly do is just choose the function. And then we have to plug it in and see that it works for our requirement that the change in the potential energy be equal to the negative of the work done by that conservative force. Now, just to show that you could make other choices, let's make a not so recommended choice. And then we'll talk, though, that maybe it wasn't such a bad thing after all. So a not so recommended choice. And it's only not so recommended just because it's going to force you to carry extra terms along, is I could have chosen to define my gravitational potential energy to be m times g times y plus, we'll just call it y naught. This is just some number as long as it has units of meters. And let's go ahead and do the same test and see, does this work? So what we require, so we are demanding that the change in gravitational potential should be equal to the negative of the work done by gravity. Okay, that bit we found. That was mg y final minus y initial after we took care of the two minus signs on the right. Let's take a look at the left. On the left, my final potential energy would be mg y final plus y naught for this choice. I'll be subtracting mg y initial plus y naught. But hey, check that out. They cancel. So it still works. So you could totally make that choice. And in fact, what that actually means is that since we can just go ahead and add or subtract some arbitrary amount, that's the same difference as choosing where to put y equals 0 in the problem. So with this expression for gravitational potential energy, we are free to choose where y equals 0. Now, I'll say that probably about 95% of the time when you do problems that involve gravity, you're going to probably want to put y equals 0 at the lowest point in the problem. By doing that, that just makes all of your potential energies positive, and that makes things a little easier. Sometimes, however, other choices are more convenient, and you just sort of learn those as you go along. But it's never a bad choice to put y equals 0 at the bottom. Okay. And similarly, we saw that the spring force if you remember, we saw that the work done by a spring was equal to minus 1/2 k x squared, or minus 1/2 k delta s squared, where we made this choice for the special coordinate system where x equals 0 at equilibrium. And here's where we didn't make that choice, but just said that delta S is the stretch or compression. The usual choice for the potential energy for a spring then is just 1/2 k x squared if we're using the special coordinate system where x equals 0 at equilibrium, which is probably what you'll do most of the time. Or 1/2 k delta s squared if you're not. But you'll probably prefer this one here, I'm suspecting. Now, again, you can make other choices. You could, for instance, choose to add, say, plus 82 joules, for instance. That's totally a choice you could make. But all that's going to do is when you say, oh, so the change in the potential energy is equal to the negative of the work done, all that does is that just takes that additive constant and cancels it back out. And when you're working with springs, it doesn't ever really help. All right. So with that defined, what that allows us to do now is come up with the work-energy theorem. Which is just a riff off of the work-kinetic energy theorem that we saw before. So we'll start with the work-kinetic energy theorem that, remember, said that the net work on an object was equal to the change in kinetic energy. All right. What we can do, though, is we can take the net work and we can split it up. We can say that it's equal to the work done by non-conservative forces plus the work done by conservative forces. That pretty much covers every possibility. It's either one or the other. All right. So then that will be work non-conservative would be equal to delta K minus the work done by conservative forces, but recalling that the work that minus the work done by a conservative force is equal to plus the change in potential energy, we get that the work done by non-conservative forces is equal to the change in kinetic plus the change in potential energy. And if we recall that the total mechanical energy was the kinetic plus the potential from the natural money video, we can finally take this to the work done by non-conservative forces is equal to the change in mechanical energy. All right, so let's go ahead and take a look at a couple of examples here and see what we can learn from that. All right, so I find it very helpful anytime that I look at a new concept in physics. I always like to go back to the basics and think about what happens if you throw an object. So we've already studied this both through the lens of kinematics and dynamics, so we know the answer. But hopefully now it'll be a little easier to do. So let's say we have a 5-meter high cliff, like so. And then let's say you throw a ball. We'll start with horizontally here at 10 meters per second. And we know it's going to follow some sort of a parabola like that. And what I want to know is the final speed just before impact. And this is actually super duper important. We know what the final speed is when it hits the ground, right? It's going to be 0. But the ground is going to be doing all sorts of non-conservative work on the object with non-conservative forces that may be basically impossible to model. So just like before when we would do ballistics and kinematics and we would say we don't really want to think about those forces, so we'll look at just before impact, we're going to be having the same kind of requirement here. All right. So let's just go ahead and take a look at this. We can take our work energy theorem here now and say the work done by non-conservative forces is equal to change in kinetic plus the change in potential. Well, here we're neglecting air resistance, so there are no non-conservative forces. This will be K final minus K initial plus U final minus U initial. So we can rewrite this as K final plus U final equals K initial plus U initial. Or if you prefer, and this is why we say energy is conserved, the final mechanical energy equals the initial mechanical energy. Now, when I do these sorts of energy conservation problems, I like to, as I sort of previewing the natural money video where we made a table of all the money before and after, I like to make similar tables keeping track of all the energy before and after. So we'll say final, initial, and then we'll list all the forms of energy we can think of. Well, that's going to be kinetic and gravitational potential, and yeah, we're pretty much done. So the final kinetic energy is going to be 1/2 mv final squared. The initial kinetic energy is 1/2 mv initial squared. Now we got to think about our gravitational potential energy. We are free to choose where to put our coordinates. we could make them literally anything we want. But I think what will be most helpful here is if we decide that y final equals 0 meters. By doing that, that will make the gravitational potential energy at the end 0. This will still leave us with y initial equals plus 5 meters. That's at least a positive number, so that'll give us a positive potential energy. So then we can go ahead and say, this is mg y final, mg y initial, but y final being 0 makes the final potential energy 0. Now, I could have chosen some other set of coordinates as long as up is positive here. I could have made, say, the top equal to 0, then that would make the bottom equal to negative 5 meters. You'll get the same answer, but I think it's less intuitive. All right, so anyway, we've filled out our table. So now what you just want to do is add up the after and the before columns and equate. 1/2 mv final squared equals 1/2 mv initial squared plus mg y initial. And thankfully, since I never specified what the mass was, we happily discovered that the mass cancels. And to solve for the final speed, we'll just have to multiply through by 2 and take the square root. So let's see, multiplying through by 2 gives us v final squared equals v initial squared plus 2g y initial. Then take the square root, v final equals the square root of v initial squared plus 2g y initial. All right, so we can go ahead and figure out what that is. We can stick in the numbers and get 10 meters per second squared plus 2 times 9.8 newtons per kilogram times 5 meters. And we remember that dimensionally a newton per kilogram is the same difference as a meter per second squared. So this is meters per second quantity squared. So this is meters squared over second squared. Here I have a meter per second squared, but I'm timesing that by meters, so I still have meters squared over second squared. So we have compatible units here. That's good. Whenever you add or subtract, the units have to be compatible. They're meters squared over second squared. I take the square root, I end up with meters per second, so yay, the units check. And I get something faster than what I threw the object at to start. I get 14.1 meters per second, so that seems plausible. All right, now what I would like you to do is I would like you to repeat this exercise for 2 new scenarios. In one scenario, I would like you to think about what if I threw the rock up at a 45-degree angle, still going at v initial equals 10 meters per second. And I also want you to think about what if I threw it down at a 45-degree angle, again with v initial equals 10 meters per second. So go ahead, pause the video, work on that, and get back with me. All right, well, I hope you didn't throw a brick through your viewing device, but you should have gotten 14.1 meters per second for those other 2 times too, right? The kinetic energies only depend on the speed. So sure, I changed the direction, but that did not change the initial kinetic energy. That also didn't change the final kinetic energy. But clearly, the initial and final velocity is different. The direction that the velocity vectors are pointing changes. And also, so is the trajectory. So for instance here, yeah, it's a parabola, but it's going to look like that. And this one, it's a parabola, and it's going to look like that. Just before impact, all of these will be going at 14.1 meters per second, but they won't be pointing in exactly the same direction. Also, they will have been in the air for different amounts of time. This one will have had a shorter hang time. This one will have had a longer hang time. than the initial one. So this reveals a key limitation of energy analysis. With energy analysis, it will always be the case that you throw away trajectory, so what path the object takes, and time evolution information. By time evolution, I mean where some object was at a particular time. So in this case, the total hang time, or even just plain like what time you were at the top of the trajectory or anything like that. That information is not, you cannot get that information by energy analysis. You just can't. There are good reasons for that, but why that is gets a bit beyond the scope of this treatment. It's related to a thing called Nether's theorem, but this is the cost. So the pros of doing energy analysis is if you don't care about the trajectory or the time evolution information, it'll work the way through the problem like a hot chainsaw through butter. Now, if you do care, you're kind of stuck. You have to, so if you care, so if you need these, you either have to do what we call exploit a constraint. I'll show an example of that in the next example. Or you just plain have to do Newton's second law. But even there, you might get lucky and only have to do some of it as opposed to all of it from before. All right, so let's go ahead and do another example. So this time we'll do an inclined plane with friction to show what happens if a non-conservative force is also present. Now, if a non-conservative force is also present, this will mean that you'll probably have to do some Newton's second law action, but the hope is that you won't have to do as much as you did before. I'll show you what I mean by that. So let's say that I have box here, there, and we're going to let slide down 5 meters. We're going to say the initial velocity is 0, so it will just barely nudge. We'll barely nudge it to get it going. And again, same deal. At the end, I want to know what is V final equal to. All right. Actually, let me call this delta S instead of delta R, just to avoid a little bit of confusion. So our displacement down the ramp is 5 meters. I'm just going to go ahead and, looking ahead, that gravity being a conservative force, I'm going to go ahead and define where y initial and y final are. I'm going to put y final down here as being at 0. And y initial here is going to be equal to delta S sine theta. So that'll be 5 meters times the sine of 37 degrees is basically 3 meters. All right. But actually, we'll just leave it like that. Yeah, we'll leave it like that. All right. Now, the full-blown version of the Work-Energy Theorem says the work done by non-conservative forces is equal to delta K plus delta U. So let's rearrange. So work non-conservative equals K final minus K initial plus U final minus U initial. All right. So I'm going to rearrange that to be K final plus U final equals K initial plus U initial plus the work done by non-conservative forces. Now, with the work done by non-conservative forces, we've got no choice. We have to do Newton's second law on this. No ifs, ands, or buts. Or at the very least, we have to come up with expressions for the work. But you'll see that in this example, we'll have to do some Newton's second law. At the very least, first thing we're going to need to do is draw a free body diagram. So we'll go ahead and follow the first law of inclined planes and tilt our coordinate system to match. All right. Let's draw a free body diagram. So we've got the normal force perpendicular to the ramp, the force of kinetic friction parallel to the ramp, and sorry, I forgot to mention here our coefficient of kinetic friction is 0.25. All right. Then finally, force of gravity straight down. And by the second law of inclined planes, this angle is also our angle theta, the angle for the ramp. All right. While we're at it, we'll just note that this much here is F. Oops. Let's do a better job of dropping that perpendicular. There we go. FGX, FGY. Great. And let's move our kinetic friction to be next to that arrow. Good. Alrighty. Clean that up a bit. FGY. Okay, there we go. All right, so let's find the work done by the normal force. In this case, the displacement is down the ramp, and the normal force is perpendicular to the ramp. That makes that a right angle. Forces that are at right angles to the displacement do no work, so the normal force does no work. Yay. Gravity is conservative, so we don't have to find the work done by gravity like we did the last time we visited this sort of a problem. But we will have to find the work done by kinetic friction, and that's going to take us a second. So same deal here. Delta S pointing down the ramp. Force of kinetic friction pointing up the ramp. So that makes the angle phi here 180 degrees. So the work done by kinetic friction will be equal to Fk times delta S times the cosine of 180 degrees, but the cosine of 180 is -1, so we have minus Fk delta S. And from the model of kinetic friction, we can say that's minus mu k times the normal force times delta S. And now we're stuck. We do have to do a little bit of Newton's second law here, and this often happens with non-conservative forces. In this case, I still need an expression for the normal force to properly account for friction. But what this does mean is we can say F net equals ma. So I only have to look in the land of y. In the land of y, we've got the normal force pointing up. And we've got the y component of gravity pointing down. Well, that's the force of gravity times the cosine of our ramp angle, theta. So equal m a sub y, which is a sub y is 0. So the normal force is equal to force of gravity times cosine theta is mg cosine theta. Okay, so with that bit of information, then we can go and substitute that in for the normal force there to get that the work done by kinetic friction is minus mu k mg cosine theta. Oops, and I dropped a delta s, minus mu k. There we go. Mu k mg delta s cosine theta, which is not this angle here. That's the ramp angle. So in this case, we had two different angles we had to keep straight. All right, so how does this look when we make our tables? It's still going to be the same deal. We have final and initial. And now we list all the forms of energy we can think of, kinetic, potential, but now we'll also have to put in our variance here, which is the work being done by the non-conservative force. And if we take a look at how we wound up writing this, we see that we're going to be putting the work done to make the books balance. We'll put the work done by the non-conservative force on the initial side. It's not really a form of energy, it's just work, but it's something we have to do to balance the books. So usually when I make these tables, what I do is I just plain make a blacked out square like that, so I don't write anything on the final side, and just write my work done by non-conservative forces on the initial side. All right, so my final kinetic energy is 1/2 mv final squared. My initial is 0 because we just barely nudged it. My final potential energy is 0 because I chose to put y final equals 0. This is going to be mg y initial, but y initial we said was delta s times sine theta. So this is mg delta s sine theta. And now I'm going to have my variance here. My non-conservative work is minus mu k mg delta s cosine theta. All right, so again, same deal. I just add up the columns. In this column, all I've got is 1/2 mv final squared. And over here, I have mg delta s sine theta minus mu k mg delta s cosine theta. Well, the first small favor is that the m's cancel, which is good because I never gave you the mass. The second small favor is I can pull out a g and a delta s from everything. So g delta s times sine theta minus mu k cosine theta. So then I'm just left with timesing through by 2 and taking the square root. So I get that v final equals the square root of 2g delta s sine theta minus mu k cosine theta. So we end up with the square root of 2 times 9.8 newtons per kilogram times 5 meters times the sine of 37 degrees minus 0.25 times the cosine of 37. Take the square root. All right, so as usual, we'll note that that's dimensionally the same thing as meters per second squared. So meters per second squared times meters gives me meters squared over second squared. Take the square root gives me meters per second. It all works out. And I get 6.26 meters per second, which is what we got when we did this before, but it was still definitely easier. All right, so with that, there's just one last thing to take into account, and that is where did the energy go? If we wanted to, we could do a better job of balancing this out. That's going back to remembering that the thermal energy is the sum of the kinetic energy at the microscopic level plus the potential energy at the microscopic level. And so if we want, we could put that in as well. We can say that the work done by non-conservative forces is equal to delta K plus delta U plus delta E thermal, if we're wanting to keep track of where the internal energy goes. Alrighty, so in the next video, we will go ahead and take a look at how to interpret potential energy graphs and see what that tells us about the motion, and also to see how we can get forces from potential energies. So we'll catch you over there.